can memory fragmentation be avoided? Have you ever wondered what happens to memory in your computer when programs are running? One common issue that arises is memory fragmentation. So, can we avoid it altogether? Let's break it down. Memory fragmentation occurs when free memory is split into small, non-contiguous blocks. This makes it tough to allocate larger memory spaces when needed. It mainly happens due to the dynamic allocation and deallocation of memory blocks of different sizes. As programs start and stop, gaps can form between used memory regions. While we cannot completely eliminate fragmentation, operating systems have several strategies to minimize its effects. One popular method is paging. In this approach, memory is divided into fixed-size blocks called pages for processes and frames for physical memory. Since pages can be placed anywhere, paging removes external fragmentation. However, it may lead to some internal fragmentation if the pages are larger than necessary. Another technique is segmentation. Here, memory is divided into variable-sized segments based on logical divisions like code, stack, and heap. This method reduces internal fragmentation but can still face external fragmentation challenges. Some systems combine segmentation with paging, known as segmented paging, to improve efficiency. Virtual memory is another useful concept. It allows the operating system to use disk space to extend physical memory. This means processes can run without needing large contiguous physical memory, which helps reduce fragmentation pressure. Memory pooling is a strategy where fixed-size memory blocks are pre-allocated. This can help avoid frequent allocation and deallocation of variable-sized blocks, thus reducing fragmentation. Efficient allocation algorithms also play a role. Methods like first fit, best fit, worst fit, and next fit help determine where to allocate memory blocks. These algorithms aim to minimize fragmentation during the allocation process. Some systems utilize garbage collection and defragmentation. This involves periodically compacting memory by moving allocated blocks together. By doing this, larger free contiguous spaces are created, which reduces external fragmentation. However, this can introduce some overhead. Lastly, programming practices can help too. Allocating memory in larger blocks, reusing memory efficiently, and timely deallocation can prevent fragmentation from building up. Different operating systems emphasize these techniques based on their design goals. Real-time operating systems often use memory pools and fixed-size allocations to ensure predictable performance. General-purpose operating systems like Windows, Linux, and macOS, relying heavily on paging, virtual memory, and sophisticated allocation algorithms to manage fragmentation while maintaining flexibility and performance. In summary, while memory fragmentation cannot be entirely avoided due to the dynamic nature of memory use, operating systems apply a combination of management methods and allocation strategies to minimize its impact.